Yes, so I'm talking about Java 8 here, in particular lambdas and to small degree streams, but mostly from my perspective, which is to do with low latency. So what are some of the performance considerations that you come across when looking at lambdas? My name is Peter Lawrey, and I've been working with hedge funds for and investment banks for about 7 years and 23 years in IT. I have the most answers for JVM and Java on Stack Overflow. So believe me, I've seen every kind of question. So there are no stupid questions. Although if you can come up with a more stupid question, I'll give you some sort of prize. Founder of the Performance Java Users Group, and I'm also a Java champion. There's about 150 of those. I have a company, 3 full-time, 3 part-time employees, and we specialize in helping companies migrate to high-performance Java, particularly Java 8. So, in fact, most of our clients are, even though we're a Java shop, most of our clients are not Java shops. They don't have the in-house expertise that they would like if they were going to switch to Java. We did our first large Java 8 project in production December last year, so nearly a year now. And we also sponsor a number of open source projects on OpenHFT. Some of these are now Java 8 specific, so you can see some of the enhancements they've used to use Java 8. We have a couple of commercial products. One is Chronicle Enterprise, which is very much around data grids and microservices, high performance microservices. And also Chronicle Fix, which is a low latency fix engine. And for a new client, we usually offer a 1-week workshop where we take a new project that they're going to launch, and we work with them over that week to create a prototype of that system, making sure that all the infrastructure and a lot of the design principles are heading in the right direction. So these are our products. Well, software products. So all the ones in green are open source and free. So you can have a look at the code, you can contribute, read it, use it for inspiration, or whatever you like. The ones relevant to this talk in particular is Wire here. Wire uses lambdas extensively, and I've got some examples in the code. To tune this, we had to look at how lambdas are actually implemented and optimized in Java 8. We also use lambdas in Engine to a smaller degree, but one of the things we do, which is interesting there, is that we use lambdas for distributed computation. So you actually have a client, it uses a lambda. That lambda is serialized, executed on the server, and then the result sent back to the client. So it's a very simple way of writing a snippet of code that's actually run, and you don't need to know where it's even run. It could be run on another machine. So just to mention what we've done in the microservices space, this is the Enterprise Edition. What we can do is you can drop in Java files and or store them in memory, and they're compiled in memory and loaded in real time. If that service is already running, it will serialize the existing service, deserialize it using the new code, so you can migrate it while the application's running, and you also have the option of shutting down a component. So these are fairly standard microservice capabilities. What we're looking to add is the ability to run test components in production while the production system is still running and not interfere with it. So you can bring in new versions of software and have them running concurrently, see how they operate, get comfortable with the new version, and then basically flick a software switch, and it will switch from having production traffic going to your existing instance to running it off your new instance. One of the benefits in the low latency space is that code takes a certain amount of time to warm up. So you don't actually want to be trading off a cold application. That's one that's only just started or one that's just started new code. So you actually want to see the code running for a period of time before you start trading off it to ensure that a decent portion of that code has actually been compiled. So I was going to do a little demo, but since I'll have to show you this later, but because we're not running on my laptop. But in this demo, which is available on our website, Chronicle Q, you can download this. And in this demo, it has two engines. They're spitting out messages which are being written to a Chronicle Q. This has been throttled at 1 million events a second, just so that you don't use up too much disk space. And then this is being consumed by another process. At the same time, the data is being replicated. For the purpose of this demo, it's been replicated over loopback, but obviously it can be replicated across a real network, and then being consumed by another remote process. So when you run this, it's actually writing every message twice, because there's two copies, one copy here and another copy there. And on my laptop, on Ultrabook, on battery power, I can get pretty close to 1 million a second. And on a decent server, you can get to about 2.5 million a second. But don't forget, it's writing everything twice, so it's quite a lot. And the other thing is that this is only writing with one thread. There's two threads here. There's one consuming thread. So we're not actually using a lot of threads. Partly because we expect that this demo will be run on small machines. When you run it on servers, you can actually use all of the threads on the server. One of the things to watch out for if you run it is that it uses up disk space pretty fast. So try to avoid running out of disk space. But moving on to the topic. The agenda, what do I consider to be low latency, because it's not a well-defined term, but used quite a lot. What do I consider to be ultra-low GC rates, and why would you want to have such a thing? How does Java 8 help? What are some of the advances in Java 8 in terms of optimization which help in this space? And why it's important to optimize for latency rather than throughput, because there's often a lot of focus on throughput when in fact there's a lot of advantages in optimizing for latency instead. So what do I consider to be low latency? It's used in a broad range of contexts, but mostly it means that you care about latencies you can't see. So in the web space or in the GUI interaction space, if a latency is too small for a user to see, then that's usually small enough. How small that is, probably it doesn't matter. As long as it's too small for a user to notice the difference. But in the low latency space, you actually care about latencies which are too small to see. And this implicitly means the only way to know whether you're achieving these latencies is through measurement. Your application has to measure itself, or you have to have a component attaching to your application to measure it to see that you're achieving the latencies that you actually require. Yes, so that's a very broad category. Even that's very broad, because this can mean 10 milliseconds, it can mean 1 millisecond, it can mean 100 microseconds. Some of our clients have systems where they're looking to respond in 25 microseconds in Java. There are people who are not using Java are looking to respond in 1 or 2 microseconds. That's a packet coming into their network to the time a packet goes out. You can't do that in Java because the network card itself takes that much time. So you haven't got anything you can do in Java in that time. But if you're looking at time frames of 25 to 100 microseconds, these are the sort of applications you can write in Java. So this is similar to my example yesterday, but instead I'm talking about different kinds of memory access. So one of the ways to improve performance is to try and use, when you're accessing data, either reading or writing, you really focus on trying to use the faster accesses. So you can do the same operations, but in reality, those operations take a fraction of the time. So I've included here the speed of light, the amount of time this takes in terms of the speed of light through either a copper fiber or regular fiber. Now, the reason I mention this is that the speed of light through a medium depends on its density. Technically, it's optical density. And in fact, the optical density of both copper and fiber is about 1.5, which means it takes 1.5 times longer for light to travel down through that medium. Now you might think, so one of the terms people often say in high performance is you can't play with the speed of light, but actually you can, and that's because the speed of light through a fiber isn't actually the same as through a vacuum. And they actually use this. There's a microwave link between Chicago and New York, and because air has actually got a density much closer to a vacuum, you can get close to the speed of light in a vacuum. So if you send a signal via microwave link from Chicago to New York, it can get there 2 milliseconds before you can send light down a fiber cable. And this 2 milliseconds is enough to make quite a lot of money. So typical user of this microwave link is paying millions of dollars a year. One of the downsides of microwave links, though, is that it doesn't work when it rains. So it's something to take into account. You have to hope for good weather. But in particular, where the most common thing that you can speed up actually is not in here, and that is the difference between SSDs and spinning disk. This is the most common issue that comes up again and again. People are using spinning disk. That is great for cost, capacity, reliability, but when it comes to speed, spinning disk fundamentally is restricted by the speed at which the disk spins, and the disks can only spin so fast and still achieve the capacities that they have. And in fact, as you go up faster speeds, they lose their capacity, so you don't get that same advantage. Now, SSDs have no moving parts, and they're often partitioned, so they can handle multiple requests at the same time. A typical high-performance SSD can handle about 16 requests simultaneously. And as a result, the number of IOs you can get out of an SSD, even a modest one, can be between 100 and 1,000 times that of a spinning disk. So one easy way to speed up your persistent access is to use either a spinning disk or in some cases a hybrid drive. So a hybrid drive can also give you that variation where you can get the performance of SSDs but the capacity of spinning disk. So it's often the easiest thing to speed up. Surprisingly, this is not always the business point of view or the client's point of view, and I'm often amazed how much money they're willing to pay us to work around this problem on the software side, when for the 10th of the cost they could have just upgraded their disk subsystem. Nevertheless, why does consistency of performance matter? The main reason for consistency of performance is that not only do users remember the worst experience they ever had, so it doesn't matter that, say, a web page is fast most of the time. If it's slow occasionally, that's what they will remember. You get similar problems in trading systems or any kind of system that's under high load, because what happens is it's the worst performance. That's the one that's going to cause the failure. That's the one that's going to lose your money in a trade. So in fact, focusing on the distribution of your performance, and in particular on your worst performance, really does matter. Where does ultra low latency GC come into that? In Java, some people sort of treat garbage collection as somehow a necessary cost of using Java. In reality, you can tune Java so that you use less and less objects, until what happens is you get to the point where it no longer gives you any benefit. But in reality, with effort, you can do it. And in fact, the sort of systems some of the systems that I work on, their target is 1 gigabyte an hour, which is about 30 kilobytes a second. And at this rate, you can run for an entire day, to fill up a 24 gig Eden space. That's basically where that number comes from. So you can run for an entire day without any minor collections. And it is actually possible. Now, it's not as easy as not having to worry about these things, but you should never take the assumption that if you've got an application that's producing a lot of garbage, that this is necessary. It may be necessary if you have no control over the code that runs it, but if you have control over the code and you're writing that code, then you can reduce your garbage to dramatically. So the Eden space is where objects get created at first, then they're copied backwards and forwards from the survivor spaces. And once they reach the tenuring threshold, because they've been copied that many times, they go into the tenured space. The tenuring threshold is 4 by default, but for reasons that are not entirely clear, if you touch pretty much any of the parameters, it just changes the default to 15. So that's why most people think the default is actually 15, but in reality, if you touch none of the parameters, it's 4 by default. And in fact, you may find that reducing the tenuring threshold could make sense. One of the things that's also worth remembering is that if you double the Eden space, it takes twice as long to fill up, which means you get half as many GCs. So in many cases, you actually want to make the Eden space as large as possible, but not so large that your GCs are taking too long, right? So you've got this trade-off here between how often your GCs occur and how big they are when they do occur. One of the benefits, though, of having a larger Eden space is that objects stay for longer in the Eden space, they stay for longer in the survivor spaces before they go into the tenured space. So they're much more likely to die young, these are the new size or young generation. They're much more likely to die young, they're much less likely to end up in tenured space. And as most people know, is that the full collections, the one that clean up the tenured space, they're the ones that really hurt you. And again, even if you've not tuned the system to not do any GCs, it's very common to try and tune the system to avoid any full collections, like have a very limited number of full collections per day, because they're the really expensive ones. And if you're not getting any objects going into the tenured space, you never need to clean it up, or if you're getting a very small amount going into the tenured space. Main difference between Java 7 and 8 is this metaspace was added. Metaspace is tuned differently, but largely it's like a perm-gen version 2. It has the same purpose, it does much the same thing. So even though they were talking about they were going to get rid of metaspace, in reality they renamed it. And the main difference is that tuning parameters are different names, which is probably why they thought, let's not confuse people and call it perm-gen, we'll call it something else. But it has the same purpose. Oh, and it has a max metaspace, and that's one big difference, is that the max perm-gen in Java 7 has a default value. So you can run out. So particularly for web-based applications where you load up lots of code, you can run out of perm-gen, and this can cause an out-of-memory error even though your heap might have plenty of space. In Java 8, by default, there is no max metaspace. So if you don't set it, it will grow until you run out of memory on your machine, potentially, right? That's if you keep loading in lots of code that never gets cleaned up. So you may find that actually in production it makes sense to put some limit on it. There is probably some point that if you reach this amount of memory, you don't want it to just keep growing. You would rather the application fail. Don't know what that point is. It may be close to your main memory size, but you probably don't want to let it run unstopped. So what are compressed OOPs? Now, one of the misconceptions about 64-bit applications is that you have to use 64-bit references or use 64-bit pointers. In C, this is true. C++, 64-bit applications can only use 64-bit references. But in Java, it uses the fact that it's a virtual machine to allow it to do transformations on references. And in particular, what it can do is it can use the fact that each object has to be on a multiple of 8 bytes to not actually store the lowest 3 bits of the pointer. Because it's a multiple of 8, the lowest 3 bits are always 0. It doesn't have to store this. It does if you only have a small heap, but if you have a medium-sized heap of between 4 gigabytes and 32 gigabytes, it makes use of this to allow you to address 32 gigabytes, but only using a 32-bit reference, which wouldn't otherwise be possible. So in fact, most 64-bit Java applications are actually using 32-bit references if you're in Java 7 or later. And this can save quite a lot of memory. So one of the big advantages from going from Java 6 to 7 was just improved memory consumption. Although later versions of Java 6 had this as an option, but you had to turn it on. Java 8 added the ability to change the alignment. So I mentioned it was an 8-byte alignment in Java 7. In Java 8, you've got the option to make it 16-byte aligned, which now means that you can address up to 64 gigabytes still using 32-bit references. You can make it 32 bytes and go to 128 gigabytes, but most of the feedback I've had is that that's not worth it. The cost of all that padding in each object is worse than just using 64-bit references. And in fact, this setting, whether it does this or not, appears to have changed in different updates. So even the JVM designers couldn't decide whether it made sense to do this always. So you might find that you want to play with this to see if you have a heap size around here, you may want to play with this to see whether it helps or not. So I just talked about that already, and this okay. So what's another reason for reducing your GC? And that is that apart from having less pauses and also making it easier to tune your GC because you're having to struggle less to get it to clean up the garbage, is that your caches work more efficiently. So as we saw in a previous slide, no, it's not in this slide, on another presentation, right? Okay, your L1, your CPU has an L1 cache, and that L1 cache is small but very fast and close to the CPU. Then you have an L2 cache which is bigger but slower, and you want to, so you don't want to use your L2 cache as much as possible. You want to stay in your L1 cache. But then you have an L3 cache which is much bigger. It's often the amount that's quoted for a CPU because it is bigger, but the problem is that it's shared, which means that it's a contended resource. You don't really want to be accessing your L3. And the last thing you really want to be doing is accessing main memory, because that is a shared resource. Only one thread can be attempting to really access that main memory at any one time. Some of the servers allow you to go to 2, but it's kind of limited because you're going to have maybe up to 18 cores, 36 threads. You want to avoid hitting main memory if possible. Now, one of the things that doesn't help is if you're constantly filling your memory with garbage, which is in fact what the garbage will do. If you're producing in the order of 300 megabytes a second of garbage, which is considered reasonable for a web application, then you're actually filling your L1 and your L2 cache with garbage every millisecond. If you try and access data you accessed a millisecond ago, it's not going to be in your L2, it's now going to be in your shared L3. So your application is going to run slower. And this is between GC pauses, not just on the GC pause it's going to be slow. So it has a penalty, you're paying a tax all the time by creating lots of objects. And this is true in other languages as well. If you reduce the amount of objects you create, you can improve the performance in just about any language. Okay, so if we reduce our GCs and we're not getting even minor collections, does that mean we won't have any pauses? Well, actually that's not the case. A lot of pauses, and certainly by number, most pauses are not caused by the GC. In fact, most pauses are very short and they're caused usually by the scheduler or some sort of interrupt. Now, they're usually too small for you to care about, but in reality, what happens is when you reduce your GC pauses, you still see an extraordinary amount of jitter in your system. And that's because of all the other things that go on to interrupt your application. These are not recorded by the JVM, they don't come out in the GC logs, but nevertheless your application is being paused. And I have a simple test program you can run called Micro Jitter Sampler. And if you run that, you will all it does is spin on nanotime. It just keeps giving me the time, give me the time, give me the time. And whenever the time is it jumps by more than 2 microseconds, it records this. What you actually find is that on some machines, you will not only see 5 millisecond jumps on a box that's otherwise idle, it's not GCing, there's no cache misses, no memory accesses, all the process is doing is just timing itself. And yet the schedulers come in and just stop the program for 5 milliseconds and then go on, oh, don't seem to be doing anything else, I'll run you again. And then their application runs up. Now this is on a untuned system, but some systems will actually see 10 milliseconds, 20 milliseconds, 50 millisecond pauses. Some MacBooks, for example, will show 50 millisecond pauses. Some virtual machines, it's very common for a virtual machine to have 50 millisecond pauses, where the application just stops for no particularly good reason and then just starts up again. So one of the things you do find when you reduce your GCs is you stop blaming the GC for all the pauses in your system, because actually it's not the cause of, certainly by number, it's only the cause of some of your biggest pauses. Although you also have I/O delays to consider. So in reality, what tends to happen is if you're dependent on a database, you actually find that the database has even bigger pauses than your JVM does. So if you're using a Java application as a front end to your database, usually the best way to improve performance there is to try and bring as much data into the JVM as possible, so you're using the database as little as possible. So how does Java 8 help in particular, because I keep talking about garbage, is it has two features. One is that it can automatically, for not what's called a non-capturing lambda, it will automatically cache the object that's associated with that lambda. And another thing it has is an optimization called escape analysis. And what escape analysis can do is take an object and put it on the stack. And in fact, it actually unbundles the object, and all of its fields become effectively like local variables. So let's have a look at this example of, now you could have written these as anonymous inner classes, but one thing about anonymous inner classes is it will, whenever you call new, it was always creating a new object. But what you can do with, in particular, like here, this is a non-capturing lambda. It doesn't capture anything in the context. This is something that gets pulled in, but only when this code is run. So because it's a non-capturing lambda, every instance of this object it knows is the same. And in fact, it is defined in the specification that this will, even though this is an object, it will only create one the first time. After that, you always get the same object. And this reduces the amount of garbage that it calls if it gets called repeatedly. Now this one, on the other hand, is capturing system.out and adding it into the Lambda. This is a capturing Lambda, even though it does more or less the same. It does the same thing as this one, sorry. So these two do the same thing, except this is capturing, this is non-capturing. Now, one of the consequences of this, apart from performance, is when you do comparisons like this, right? So this is the capturing, this is the non-capturing. The capturing one, every time it's called, creates a new object, which means if you do a comparison, you get false. But for the capturing example, because it's a bit like the boxing cache for integers or the string literal pool for strings, is that you end up getting the same reference. So this will print true. One of the obvious differences is if you put these two into a set. In this case, this will become a set of 2. In this case, it becomes a set of 1. So there's a sort of indirect consequence of this optimization you need to be aware that you will come across at some point. In particular, the more frustrating thing is that when you have two pieces of code that look exactly the same, do the same thing, and you do it equals on them, it still says they're not the same. They're different objects. I have no idea. I pretend I know nothing about Java code, unfortunately. Okay, so another thing that we do with Lambdas in our libraries is support serialization. We need to do that so that we can distribute the Lambdas. And this is where having the more restrictive scope of Lambdas is very handy. It doesn't just capture this because it's defined to. So anonymous inner classes always capture this, even if they don't use them, right? The only time they don't capture this is if there is none, if it's in a static context. But if there's a non-static context, it always captures this. So when you attempt to serialize it, it tries to serialize the this, even if it's not used. And if that's not serializable, it'll blow up. Or worse, if it is serializable, you end up serializing a lot more data than you ever imagined or ever intended. So by reducing what is captured and minimizing that, that means that when you serialize it, it's more efficient. So some examples of this is the way we support serializable Lambdas is that we have interfaces. We add interfaces that are also serializable. It's another mechanism for doing this, but it means a lot more boilerplate code for the end user. In this case, it's more work for us to write the API, but then once you've written the API, there's no more work for the end user. So in this case, because it's a capturing Lambda, this will fail to serialize because it says, oh, I've got a print stream in here, which is system.out. That won't serialize. In this case, it's part of the code. So what will happen actually is this will get serialized, sent to the server, and if it's executed on the server, it writes to the system.out on the server. So what actually happens here. In this case, this has got the same bit of code as in here. The difference is because it's anonymous in a class, it captures the outer this of the class it's in. That's not serializable, so the whole thing blows up. Why would you want to serialize Lambdas at all? Well, we've got lots of examples where we do this in our class we call Redis emulator. It's not a full emulation in the sense that it's a drop-in replacement, but it's an emulation in the sense that for each method that I have in Redis, we show how we would do it ourselves. But here's an example. This method says apply a synchronous update to a key in a map. So the update is it adds a value, it looks up the key, gets that value, adds the value, and returns whatever the result is. So this is how in Lambdas you say just return whatever you get. So in this case, it takes the value, adds it, and then returns the result of this. So it's a nice, easy way of saying, I want to remotely, on wherever this data is, I don't need to know, it will send it to the server that has that data, apply the execute function, and then give me back the result I want. Here's another example where it takes a pattern, but then in the Lambda, which means on the server, it compiles that pattern, goes through all the keys, finds all the matches for that pattern, and returns a set. So it's very easy to construct your own functionality for remote execution. And last but not least, this is what we call a live query, where what happens is that this filter and map, this is very similar to what Stream does, where you can apply a filter and a map and then get the results. The difference here is that this filter and map are actually serialized and applied on the server. So what gets sent back to the client is the actual minimum amount of data that the client needs, not just all the, send all the results back to the client and let it sort out what it wants to do with that data. And in particular, what Subscribe does, which is again different to Streams, is a stream will go through a list once, or in this case, a map once. Once it gets to the last entry, it stops and it returns. What this does, though, is it will asynchronously make this call. So in fact, this method returns almost immediately. Then asynchronously makes this call for each of the elements, but it continues to do so. So whenever a new element is added or a new element matches this criteria, that comes through as well. So you get a continuous update of information. What this does is it returns a subscription object which allows you to cancel it if you don't need it anymore. So how does escape analysis help? This one's particularly useful because you don't really need to know it's doing this. It's only really annoying when you would like it to work and it doesn't, because it doesn't always explain why it didn't work. But the cool thing about this is that escape analysis allows it to work out that an object doesn't escape the method in which it's created. And if it doesn't escape the method in which it's created, it can be potentially put on the stack. And this improves the performance of both the allocation of the object, but also there's less garbage to clean up in the first place. Another benefit is that if it doesn't escape the method, it doesn't need to be synchronized. So you can use thread-safe objects, and then the locking can be eliminated. The main thing to watch out for is that escape analysis is dependent on inlining. The only way it knows it doesn't escape a method is if, in fact, every use for that object has been inlined into that method. A lot of optimizations in Java rely on aggressive inlining. So if you're having problems with inlining, or you're trying to work out why code isn't more optimal than it is, you may find that inlining is your main problem. It's not inlining something you would really like it to inline to get maximum performance. The other thing to be wary of is, while it does a good job and it does improve the code, many cases it doesn't do as good a job as if you'd handwritten it yourself. But the fact that you don't have to do much work for this to do this, and it will work for libraries you didn't even write, is actually a great thing. One of the things to play with is both the inlining parameter, which is a frequent inline size, and the maximum size for which it does escape analysis. So both these sizes are the size of the bytecode of the method that gets created. And so what it will do is, if a method is called often enough and it's less than 325 bytes, it can get inlined. Right? In fact, what happens is, if the method it would create would be less than 325 bytes, then it can be inlined. The escape analysis has a similar limit, but it's only 150 bytes. The irony being that you need inlining to get escape analysis to work, but you don't want too much inlining, or otherwise by default escape analysis stops working. And I've seen examples where you've got code that's inlined a little bit. Before it gets inlined a little bit, it's creating objects. It gets inlined a little bit. Escape analysis kicked in and said, I don't need these objects. Doesn't create any objects. Later it warms up and inlines a bit more, goes over the threshold, starts creating objects again, which is rather odd. So I actually recommend that the escape analysis setting always be larger than your inline size. And then you never get that behavior. You never get the situation where too much inlining causes your performance to go down. Oh, you still get that, but not with escape analysis. How are we doing for time? Left. Okay, so we might skip through this. But the main point to make is that if you have poor performance, then throughput is the best thing to measure, because it's a great way to hide poor performance. And that is because it averages out your worst performances. However, if you reduce latency and you improve the consistency of latency, this often actually helps throughput. Sometimes you have to trade these two off, but sometimes it can actually help as well. So the example I have here is that if a service and handles 2 requests every millisecond, or 2,000 requests a second, but every once an hour it stops for 6 minutes, right? How does this 6-minute stop affect latency? Well, if it was not to stop at all, its average latency would be half a millisecond, based on the 2,000 requests a second. However, with a 6-minute stop, the throughput drops by 20%, and now it has an average response of 0.6 milliseconds. 0.6 doesn't sound so bad. It only increased the average latency by 0.1 milliseconds. That probably sounds fine. But then if you point out, well, actually my worst case latency is nothing happens for 6 minutes every hour, that doesn't sound so good. So, so this is why when people test for throughput and they get numbers that look quite good, but users are still complaining, that's because the throughput has hidden all these bad numbers. And it does a very good job at that. So what you're actually much better off doing is looking at your latency distribution, because you're trying to solve a problem. You're trying to look for a problem. And in particular, you want to look at your worst latencies. Okay, so coordinated mission. So getting on to some examples of the API. So in Java wire, a chronicle wire, we have different adapters for different kinds of wire formats. And one of them is the JSON wire format. And so for this JSON message, if you serialize it and deserialize it, and you start to look at the percentiles, you see that the different ways you do this can make a big difference to the performance. But by the time you get into the nines, 4 nines and 5 nines, there can be a dramatic difference, orders of magnitude difference, in terms of what your worst latencies look like. And most of these are actually just due to the GC kicking in. Okay. And when the GC kicks in, it adds in a delay. So there can be some advantage in not producing so much garbage, and you'll get less worst case pauses. For reasons that I'm not entirely sure, I think it's because Jackson is actually a very well optimized library, but the binary version, usually the binary version of something, you use that for performance. But in this case, the binary form for Jackson is actually quite a lot slower. So I'm not entirely sure why you would use that. Because the good thing about the text is it's easy to read. So you can see whether it's wrong or not. So what does the code look like? This is our API. And as you can see, we're using lots of lambdas, but in fact, we're using non-capturing lambdas. And the trick to using non-capturing lambdas is to pass through as arguments anything you would have to capture. And then that avoids, the lambda itself then doesn't have to capture anything. And so what happens is all of these objects are guaranteed to be cached, and then they don't produce any garbage. So even though notionally every one of these is a different object, all of these lambdas are different objects, they will always be the same object on each run, so, as the previous run. So then you don't create any new objects. So the wire format for text and binary, output text and binary looks like this. One of the interesting consequences of lambdas is you can use it with APIs that were never written for lambdas in the first place. So that can look kind of interesting. So this is JUnit. So instead of deserializing this object that I've written, as here, I instead put the values I expect it to return and then do assertions on it. And this is the lambda form of assert equals. Another thing that's surprising, perhaps, is that lambdas, being an interface, can be implemented by an enum, because interfaces can be enums can implement interfaces. So you can actually have code where enums and lambdas can be used interchangeably, and we use this in a number of places. In particular, as you saw before, this lambda just returns a string. But in reality, what we've done is we've made YKey an interface that has a field called name, a method called name that returns a string. But enum already has a method called name which returns a string, which is just what it's called. So we don't even have to add any methods. And now we've made it that you can use enums and lambdas for the same arguments interchangeably. Enums are basically easier to debug and more efficient to serialize. So you can see in your debugger the name of the enum. In your debugger, the name of a lambda is something deliberately cryptic. And last but not least, it's all available on GitHub, all these examples. So we might have a little bit of time for questions. 7 minutes for questions. Has anyone got any? Yes?
There are cases where you would use a lambda, for example, when you create over a method.
Mm-hmm. Oh, you can iterate over the entry set as well.
Yes, but in this case, it might create garbage.
Yes, only for the maps that don't already have entry objects. Most maps already have entry objects. I'm trying to think. Yes, enum map doesn't actually have any entry objects. So when you iterate over it using an entry set, it has to create them just so that you've got some entries to work on. But most maps actually have entry objects in their data structure, so it doesn't need to create new ones.
Yeah, so the question is, usually you need to process each key and value, but you also need some context. For example, access to this object.
Yes, and that's where a capturing lambda comes into it. Now you can cache the capturing lambda yourself, but you can also make use of escape analysis. So even though you have a capturing lambda and it notionally creates an object, escape analysis can put that object onto the stack. So then you don't actually create an object at all. And in fact, not only does the object get put onto the stack, the field in that object is probably a field that you're referencing somewhere else. So it's just a duplicate of an existing field that's already on the stack, so it can actually eliminate that as well. So in fact, it doesn't even end up using any extra stack space.
When we talk about the inlining size, is the size of the calling method or the calls method?
It's okay, so the bytecode size that determines things like whether it inlines it and how it optimizes it is based on the amount of bytecode after inlining. So it accumulates this bytecode. The bytecode gets bigger and bigger. So this has a couple of side effects. So for example, synchronized methods have less bytecode than a method that the first thing it does is synchronize this. Methods without assertions in them have less bytecode. So in fact, adding assertions can cause a method to go over the threshold of where it gets inlined and end up making it slower, even though they themselves can be disabled. So it doesn't disable it and then work out what the bytecode count should be. So it adds up all the bytes. Fortunately, it doesn't include everything. Some of the older JavaScript compilers, for example, included comments. So the size of your comments and the length of your variable names would determine your inlining threshold. So it actually made sense to minimize that in the past. Some of the newer compilers are a bit smarter than that. But,
how about the try-catch clause? Can they prevent inlining?
Yes, they can prevent inlining because they add to the bytecode. But the size of the table, which is also associated with the try-catch block, isn't such a big deal. Where it can make a big difference is if you've got try finally. Because try finally, in reality, once it gets compiled, is added to every exit block or every return block. So if you've got a series of if then else's and it goes return this, return this, return this, return this, return this, and you put that in a try finally block, the entire the finally block gets added to every return statement in the bytecode. So that can be really expensive, not surprisingly, in terms of the amount of bytecode you produce and then whether the whole method gets inlined or not.
Actually, I was more worried about the logic of the try-catch, not the size.
Yeah, so the logic of the try-catch can also confuse the optimizer and prevent certain optimizations from happening. So this can have other side effects. The most common is when it comes to things like thread safety, so where it can make a big difference. So Boolean in particular can be inlined into code. So if you've got a Boolean, a non-volatile Boolean, so a common one of this is something like running, while running, do something, right? And then in another thread you go and set running to false, but you forget to make it volatile. What it can do once the code's warmed up is it goes, my thread never alters this variable. I can inline it in code. And when you inline it in code, it no longer ever even does the read. It speeds things up enormously. But then when you try and stop the thread, it won't stop. So this has two confusing consequences. If you stop the thread before the code gets a chance to optimize, it will stop because it hasn't inlined the code yet. But if you put something in like a try-catch block, it goes, oh, this is a bit hard, I won't optimize it. So suddenly it works. Or the reverse, you'll have a loop that only works because you have a synchronized or try-catch block in it. You go, I don't need this try-catch block anymore, I'll take it out. And suddenly now it can optimize it more aggressively and your threads don't stop anymore. You think, what did I do wrong? I just took out a try-catch block that does nothing, you know? Yes, so try-catch blocks can influence the amount of optimization it can do. It can also confuse static analysis tools as well. So if you use like IntelliJ or Find Bugs, they have a static analysis tool to find common bugs. But the flow control of try-catch blocks can be confusing to it, so it can miss some of these bugs that it would otherwise be able to find if it wasn't there. 1 minute. Last question then. Yes.
Is there a way to use lambdas or arrays of primitives without somehow avoiding
No, you can't at the moment. Java 10, they're talking about adding generics that support primitives. And it will actually mean adding a special type called any, which is actually will be a superclass of object and all primitives. So you'll be able to have a list of integer, a list of int, and it can be assigned to a list of any, which could also be assigned to a list of object. But the way around this is to hope that order boxing will work for you. So, escape analysis. So say you've got integers that are too large to be cached, or longs, doubles are never cached, floats are never cached, but they're very simple. And if it can do the escape analysis will kick in, then it will actually assign the entire contents of that object on the stack. Unfortunately, those objects only have one field, and that one field is the primitive. So it's effectively turned your object back into a primitive again. So this is where escape analysis could really help in that sort of situation. The other option is, of course, just to try and rewrite the code so that it uses primitives. So there are lambdas for primitives. There's int consumer, int function, toInt function, int supplier. There's one for long, there's one for double. There's none for float, short, character. There's one for Boolean. There's nothing for byte. It's a bit inconsistent as to what is already built, but you can always add them as well. You don't have to use the built-in interfaces. You can write your own. In fact, any interface which has one abstract method can be used in a Lambda, and it can be methods libraries that weren't designed for Lambdas that will still accept them.